In this video, we discuss more indeterminate forms. Indeterminate forms are actually just limits which cannot be determined directly or obviously. In the past, we learned the L'Hopital's rule that we use to evaluate such limits. The rule says to evaluate the limit of a fraction which is considered as an indeterminate form, we can evaluate a new limit, which is the limit of a fraction based on the original fraction. You can see that in the new fraction, the top is a derivative of original top expression, while the bottom is a derivative of the original denominator. So what is an indeterminate form? We cannot do this for any limit. The original limit has to be an indeterminate form. In this limit, if we estimate when x approaches a, most of the time we try to plug in a for x. Now, if our estimate is infinity over infinity or 0 over 0, for example, limit x goes to 3, x squared minus 9, x minus 3. This is an indeterminate form. The way we estimate is in the denominator and the numerator, we try to make x as close to as a 3 as we wish, so we can kind of predict the denominator will approach 0. Similarly, as x gets closer to 3, x squared minus 9 gets closer to 0. So this is considered as an indeterminate form, 0 over 0. Similarly, other indeterminate form can be estimated, determined. Either it's going to be infinity over infinity or 0 over 0. So if the limit is an indeterminate form, according to L'Hopital's rule, we can evaluate a new limit. The top differentiated according to the rule, f becomes f prime. We have simply just 2x. The bottom differentiated, simply 1. And this time we try to do the limit again. X approaches to 3, this will approach 6. So this is how we apply L'Hopital's rule to evaluate indeterminate form like this, a fraction. Now, there are some conditions we would have to check out each time before we actually apply this rule. For first of all, obviously the limit has to be an indeterminate form. Another condition is the new limit has to exist. If the limit doesn't exist, you cannot do this because this will not make sense. One more thing about L'Hopital's rule. This is just a way we evaluate this type of limit. Especially the right side, see the derivative of f, derivative of g. Don't confuse this with the differentiation rule, quotient rule there. Okay, we happen to have to differentiate to try to evaluate the limit. So this is a rule we apply to evaluate the limit. It's not a quotient rule for differentiation, totally different operation. Anyway, this is a quick review of L'Hopital's rule for indeterminate forms like this or this. So basically fraction. But what we want to do actually in this video is to see how to evaluate other indeterminate forms. First, infinity minus infinity kind. So we had infinity divided by infinity or 0 divided by 0. Now infinity minus infinity. What is this? Well, basically it is some kind of limit. Maybe f minus g. So when you try to, in the form of a difference, when you try to evaluate a limit, letting x approaching a, this thing will approach infinity, so will this. So such limit is considered as infinity minus infinity. This is one new indeterminate form. There are others. So, well, basically, how would we evaluate this type of indeterminate form? Simple. We have to do whatever it takes to turn this into a fraction. Once we come up with a fraction, then hopefully it's going to be either in the form of infinity over infinity or 0 over 0. Then L'Hopital's rule can be applied. As a matter of fact, whether it's this new type of indeterminate form or other new indeterminate forms we are discussing in this video, we all do that. We eventually all have to come with a fraction, because L'Hopital's rule applies to only fraction. Keep this in mind. Always have to get a fraction. This kind of indeterminate form usually involves a fraction. So denominator becomes 0, then you have a term or fraction approaching infinity. So expect the fraction. Now when fractions are involved, what you do is to combine fractions into a single fraction. Now you have denominator, numerator. Sometimes you don't have a fraction, you just have to try to get a fraction. Let's see one example. Well, this is a very typical indeterminate form of this sort. X approaches 0 from the right side. It's a one-sided limit. This is just to ensure that the radical expression is defined for all x. So when we estimate when x gets closer to 0, that's like a 0 infinity. The sign 0 is like a 0 infinity again. So it's infinity minus infinity. What do? Well, obviously fractions are involved. So we try to combine them. Common denominator. A lot of algebra. So we found the common denominator and combine them. You multiply top and bottom by sine. Multiply top and bottom by square root of x. So both would have the same denominator and then put them together as one single fraction. Now check. When x goes to 0, this is 0, this is 0, so the top is 0, and bottom obviously is 0 too. So this is a indeterminate form, 0 over 0. Therefore, we could try L'Hopital's rule. Sometimes I try to, when sine, power of x are present, take some shortcut. I'm not sure if this is going to work out here. What I have in mind is it may be possible we can make use of this result. This is a well-known special limited result: x over sine x approaches to 1, or sine x over x approaches to 1. If we can somehow, make use of this result, usually the work is much simpler. Worst come to worst, we have 0 over 0. We can apply L'Hopital's rule. Now, let me see if it's possible. In order to come up with x over sine x, I have to get the x first. So there's square root x. There's a square root x. Probably not now. I mean, I would multiply top and the bottom by square root x just to get the x, then divide that kind of thing. I'm not sure, it's gonna work. Give it a try. Why not? Okay, let's see. Does it work? We can try the brute force L'Hopital's rule. So what? Let me multiply top and the bottom by square x. Let's see what will happen. So we have square x sine x. And this is x. The bottom is x sine x. Now I have a sine, so if we divide, for example, top and the bottom by x, this term will turn to 1. We can only have a sine here. No, it's not going to work out. Now, I guess we'll have to apply L'Hopital's rule. Well, let's apply L'Hopital's rule. So let me continue here and copy down the limit and apply L'Hopital's rule. See what will happen. So apply is 0 over 0. We apply L'Hopital's rule. Differentiate top, get the cosine x, 1 over 2 square x. This is a product that I was very reluctant to differentiate. That's why I wanted to try some shortcut first. Didn't work out, unfortunately. This happens. So I differentiate the product, 1 over 2 square x sine plus square x cosine. Okay, check my differentiation. Derivative top, derivative bottom product. Alright, then simplify. This is a complex fraction. Here I have to multiply common denominator to get rid of the fraction here and the fraction here. Hopefully something good will turn out from this. Okay, so square x multiply through is a square x cosine 1/2 square x multiply through on the bottom, 1/2 sine. I already see something good here, plus x cosine. Alright, let me check my work first, because nothing's wrong. I just want to be sure. So I combine, and then apply L'Hopital's rule. Derivative sign is cosine. Derivative square x is the bottom. Product rule, cosine. Okay. Then I multiply square x through the half. Great. Okay, nothing's wrong. Perfect. Now I see I don't have an indeterminate form anymore. And notice when x approaches 0, this term approaches 0 because this is 0. So the top is a constant, negative half. That showing me we don't expect any indeterminate form anymore. Because in order to have an indeterminate form, you can have either 0 on the top or infinity on the top. Okay. Now, so the top will approach negative half. What about bottom? Well, this is like a 0. That's like a 0, 2. So the bottom is like a 0. Actually, it's not precise to say it's just 0. We have to be more clear about this. Meaning, approaching 0 from which side? Positive side or negative side? As I can tell, cosine is always positive when x is on the right side. This is a graph of the cosine. So cosine would approach 1 as x approaches 0 from the right side. So this is like a 1. Well, it's positive. The sine is positive too. The graph of sine looks like this. When x approaches 0 from the right side, sine approaches 0. All positive values. So these are all positive. So let me write this like sort of a positive 0. This will tell me it's a number divided by 0 is at infinity. When you consider sine, the answer is negative infinity. Alright, so very typical indeterminate form, infinity minus infinity, just combine into a single fraction to go from there. Sometimes when you have sine x involved, it's a common practice to try to see if we can make use of this special result. If not, we can always apply L'Hopital's rule. Alright, so this is how we evaluate this kind of indeterminate form when fractions involved combine. Now, rarely you see also infinity minus infinity without fraction present. What do? Well, you just have to come up with a fraction, because you don't have a fraction, cannot apply L'Hopital's rule, right? So what do? In this problem, we can rationalize. Think of this as a fraction. So we multiply top and the bottom by the conjugate. The conjugate of the radical expression is plus. Alright. The denominator is 1 times, so it becomes just square root x plus 1 plus square root x. The numerator, well, since this is multiplied by its conjugate, we can apply a formula: a minus b times a plus b equal to a squared minus b squared. So The answer is the square of this minus square of this. It's x plus 1 minus x. Let's see what we have. We simplify 1 on the top. So once we turn this into a fraction and multiply top and bottom by conjugate of the radical expression here, this limit is well, first of all, limit of a fraction. Sometimes we can apply our hope, actually generally, is worst come to worst, it's indeterminate form fraction, maybe infinity over infinity, maybe 0 over 0, no problem. We can apply Lobier's rule. Occasionally, well, like this case, with tensor fraction, this is not an indeterminate form anymore because the top is constant. So when x approaches infinity, that's infinity, that's infinity, 1 over infinity, 0. Even better, not indeterminate form. Figure out the limit much more easily. So these are the integral form in the form of infinity minus infinity. You always have to combine into a single fraction no matter what. Once you come up with a fraction, if it's an indeterminate form like this, apply Lobier's rule. If it's not indeterminate form, well, like the second example showed, even better. Just evaluate the limit. Don't even have to worry about Lobier's rule. So this is the first type of indeterminate form we discussed in this video. Next, we discuss product form. That's the difference. It's a product. 0 times infinity could be infinity times 0. Switch, it's the same thing. So what we're saying is there may be f times g. One of them approaching infinity, the other one approaching 0. So you have a 0 times infinity. What do? Well, we'll try to come up with a fraction, because only with the fraction, indeterminate form, can we apply Lobier's rule. How do we come up with a fraction? Well, let's see. Idea is in this product, one of them will approach infinity, the other one will approach 0. So it's 0 times infinity. So with the 0 times infinity, you have two options. You can flip this guy and put it on the bottom, or you can flip this guy, put it on the bottom. So if this is what we have, 1 over 0 is like infinity, so this is basically infinity over infinity. For this case, you basically have a 0 there. So either way, we can apply Lobier's rule. That's how we do it. Pretty simple. With the product, 0 times infinity or infinity times 0, you can flip one of them, put it on the bottom. Either you have this or this. When you decide which one to flip, there's something you need to keep in mind. In theory, you can flip either one, because either you get this or get this. Practice, log should not be flipped. Reason is, if you flip log, you have a 1 over log on the bottom, and it becomes more complicated when you differentiate when applying Lobier's rule. So remember, do not flip log. It's one thing. There's a trig function. trig function is always your better choice to flip. Reason is, for example, if you have a sine x times whatever, when you flip, expect 1 over sine, right? That's bad, but that's necessary. You have to flip. Well, turned out when you have like 1 over trig, it's really not that bad because of those trig identities. Reciprocal of any trig is another trig. So in this case, it'd be cosecant. So it's not really a complex fraction, which is a good thing when you later apply L'Hopital's rule. So at the bottom, you don't have to apply quotient rule or even reciprocal rule to differentiation. Alright, so those are the two things to keep in mind when deciding which one to flip. Never flip log. If there's trig, always flip trig. Alright, let's see one example. Well, this is just perfect. We got trig, we got log. This is the one we never flip. This is the one we always like to flip. That makes a decision very easy. So flip sign, put on the bottom. Actually, just showed you 1 over sine is cosecant. Now you can check x approaches 0. This is infinity. This is infinity. So L'Hopital's rule. Once we have a fraction, it's an indeterminate form, then we know what to do. So a derivative of the top is a log, is a 1 over sine times cosine. Logarithmic rule, or basically a chain rule. At the bottom, cosecant differentiated is negative cosecant cotangent. Now simplify further, see whether we can determine the limit. What I like to do is always return to just sine cosine. Cosecant actually is the same as that there. They cancel out. We see right there. Cotangent is cosine over sine. Alright. Now 1 over sine cancel each other. The cosine cancel each other. So there's only 1 over sine left on the bottom. The flip sign. It's a sign on the top. So the answer is 0. This is a very typical product indeterminate form. This approaches 0, this approaches infinity. So flip, decide which one to flip. Never flip log, flip sign. We'll see what to do with the product again in later examples. Alright, let's see one more type of indeterminate form. That's in the form of exponential. There are many actually different kind of specific indeterminate form in the form of exponential. For example, the exponent could approach 0, could approach infinity, the base could approach 0 or 1 or infinity, and now with the combination there are many. We don't need to specifically discuss each type. We can treat them just the same way. Now, so we're saying got a limit, the function f and the function g. Base is a function, exponent is a function. So it's this type. Whether this is an indeterminate form or not doesn't matter. We always rewrite. Most of the time, it's an indeterminate form cannot be determined directly. So we use this change-based formula in algebra. So change base to e can turn to exponential to base e. The advantage here is with this new exponential expression, the base is not changing anymore. Base is constant, so we just focused on the exponent. While in the original, that's a function of x, that's a function of x. Both changes. So that makes things unclear, what's going on. Okay, anytime you see limit of exponential like this, change the base. Change the base, go from here. You have always a product. So you see whether the product is an indeterminate form like this, 0 times infinity or infinity times 0. Just do it here. If it's an indeterminate form, well, flip. We talked about that. If it's not indeterminate form, of course, you can determine the limit right away. So it doesn't matter, what kind of combination. This guy approaching 1, this guy approaching infinity, this guy approaching 0, this guy approaching infinity. This is many different combinations, possibilities. But then through this approach, we don't care. Just change the base. Change the base, go from there. So let's see this example. This is like our f, this is like our g. Okay, we don't even care, whether it's indeterminate form or what. Right now, just change the base. So it'd be e raised to 1 over 3x, original exponent, copy down, and put the base inside log. Just like that. And check it here. If this is an indeterminate form, we do what we have to, flip or not flip. It's always product. But let's check it out. When x approaches 0, that's like infinity. So 1 over 0 is infinity. When x approaches 0, this is 0, this is 1. Log 1 is 0. So this is infinity times 0. Yes, indeterminate form. So we flip. Well, log, we never flip. We flip this one. So if we flip 1 over x, it becomes 1 over 3x. It becomes 3x. So it's perfect. Flip 1 over 3x becomes 3x. Or you can just say this is a product when log is multiplied by 1 over 3x. You only multiply the 1 by log, so it becomes that anyway. You don't even have to talk about the flipping at all. Regardless, we got a fraction. Check it out again to make sure it's an indeterminate form before we apply L'Hopital's rule. That's a 0, that's 0. 0 over 0, L'Hopital's rule. The bottom differentiate is 3. the top differentiates 1 plus 2x times 2. So if we send the x to 0, this will be 0. The top will be 2 over 3. The limit is 2 over 3. Alright, so when you try to evaluate the limit of this kind of complicated exponential, by complicated exponential, I mean both the exponent and the base are functions of x. We cannot estimate. It's impossible to estimate. When you try to estimate, you could be wrong very easily. For example, if you try x goes to 0, you say when x goes to 0, this is going to approach 1. This is like infinity. 1 raised to infinity power. What is that? It's not clear. You cannot say 1 raised to anything is 1, or anything raised to infinity is infinity. You don't know. Just have to do the math. Just do what we discussed here. Change the base, try to get the fraction, apply Lopez rule, get the answer. Alright, so in this video we discuss additional indeterminate forms. No matter what form, we always try to get back to a fraction. Get the fraction so we can apply Lopez rule. If the indeterminate form is in the form of a difference, try to combine into a single fraction. If it's in the form of product, flip one of them so you have a fraction. Never flip log, always flip trig if there's trig. Exponential form, change base. Change base, you always have a product here. Alright.